All right, so the next thing we're going to do is look at how we can use integration to find volumes. And it's basically a similar idea to the Riemann sums, only in this case we're going to take disks or slabs or something that has some volume and add up all those little disks or slabs, and look at the limit as the number of little divisions goes to infinity, right? So the basic idea is that you can take the area, the cross-sectional area of a given slab times some thickness, right? Times some, let's call it delta x, or it could be delta y, and that gives you the volume of that particular disk or slab. All right, well, it always helps to just dive right into a problem, and then you'll see what we mean here. So let's take a look at this cone. We have this cone, and we want to write an integral representing the volume of the cone using this slice that's shown. Okay, so we have this slice. We're slicing across the cone. It's a cone kind of laying on its side, and we're slicing it into these little discs, right? So, and the width of the disc is dx. And then we can find the area of a particular cross section, right? It's just going to be a circle because it's a cone. So sometimes I like to look at this by superimposing an axis on this. Okay, now I didn't draw that very well, because it'd be nice if it actually went through the center. So here's like the center of the cone. So this is not quite straight, but let's say that. All right, so there we have we'll call this the x-axis going through the center of the cone, and we'll call this here, we'll call this the y-axis that starts at the tip. All right, so there's the y-axis. And then you can see that the edge of the cone lies along a line, right? And the line looks like, so it starts at 0, right? So we just need to find the slope. And it looks like, okay, so if the diameter of the cone is 4, then this rise here is 2 centimeters, right? That this rise from the middle of the cone up to the line, right? So essentially this is the line, y equals, so it's basically a rise of 2 and a run of 6, so that's 2/6 or 1/3 x. Okay, so the edge of the cone lies along this y equals 1/3 x. So essentially then the distance y is the radius of any given slice of the cone, right? So it starts down here at 0. You've got basically that's the slice there would be 0 or very, very small, and then it gets bigger and bigger as we go all the way out to 6 centimeters, right? So this is the point. This right here is 6. Should probably use a different color. 6. It's easier to see that to the center of the cone, and the height here is 2. All right, so let's look at what is the area of any given disk. So the area of a disk, or I could even just say volume of the disk, right? Because essentially, if I take the area times the thickness, I'll get the volume. So I'm actually just going to write this as volume. Volume of a disk is equal to the cross-sectional area, which is essentially pi r squared. It's a circle, right? So it's pi r squared, but in this case, r, the radius, is defined by that line, right? The radius of the circle is the distance up to that line, 1/3 x, and it's squared, right? So it's pi r squared. So this is the radius of any given disk, and it's going to vary as you move along the cone. And then if we take it times the delta x, then essentially what we have is the volume of any given disk. All right, Now I can clean this up a little bit. I'm going to write it as pi over 9 x squared delta x. And now if I just take all of those little disks, right, and add them up and let the number of disks go to infinity over the interval from 0 to 6, then I have the integral, right? So I'm going to do the integral from 0 to 6 of pi over 9 x squared dx, right? So if I let the number of disks go to infinity, then essentially my delta x becomes dx, and it's of an infinitesimal width. So this is width of the disk, and this is the cross-sectional area. Okay. So now let's just do that. All right, so we can easily integrate x squared. So I'm going to write this as, I'm going to pull the pi over 9 out front, and then the integral of x squared is 1/3 x cubed. And I want to evaluate that from 0 to 6. Okay, so from here it's just all arithmetic. So let's see what happens here. We get essentially pi over 27 if I combine the 1/3 and the 9 in the denominator, and then I have 6 cubed, and then when I evaluate at 0, it's just 0. All right, so let's evaluate that. Sometimes I don't want to get out my calculator, so I know 3 cubed is 27, and I know that 6 is 2 times 3, so this is 2 cubed times 3 cubed, and my 3 cubes will cancel, and so I end up with just 8 pi. And the units here, because they gave all of the dimensions in centimeters, this is going to be centimeters cubed. Okay, units are important. So there you go. There's one example of finding volumes using integration.